Never be afraid. There's nothing which is known which can't be understood. And there's nothing which is understood which can't be explained. For over 50 episodes now, my team and I have brought you to the very frontier of knowledge in physics and astronomy. And still, our mission goes on. To present you with your birthright, an understanding of the universe. I've traveled the world seeking out a certain type of genius. Masters of not only their academic disciplines, but also at explaining their research in understandable ways. And I've bestowed upon these women and men the title of Titanium Physicist. You're listening to the Titanium Physicist podcast, and I'm Ben Tippett. And now, allez, physique! Physicists are a bunch of nerds. I'm not sure if you've noticed, but we are. The most glaring habit of nerds is that when they think no one is watching, they make stupid jokes that no one else understands. We've talked about it on the show before. Remember that episode where we talked about pasta matter in neutron stars, and how, depending on how deep you go into a neutron star, there's a different mix of protons and neutrons, and how they technically describe that mix in terms of being a spaghetti phase or a lasagna phase. And we mentioned in that episode that this is just the tip of the iceberg, and it really is. And we mentioned earlier there was something called a penguin diagram, and in particle physics you can draw the subatomic interactions in terms of imagining little particles bouncing around, and so you can draw their trajectories, and sometimes they look like penguins. And so they call them penguin diagrams. And we mentioned barns. A barn is a unit of area, and it's a joke, right? Because, you know, you couldn't hit the broadside of a barn. Yeah, so a uranium atom's nucleus has a pretty big cross-section, so they describe that area as a barn. And we mentioned the no-hair theorem. That says that for black holes, metaphorically, there's no hair. Anyway, someone should put a stop to all it, but nobody's going to because it's too much fun. So today's episode involves some of the dumbest physics inside jokes you've ever heard. The names people have given to some of the things we're going to talk about today are really silly. So, fair warning, it's going to be nuts. Today we're going to be talking about the strong nuclear force. It's the force that sticks all the protons and neutrons together in an atom. And speaking of nuts, today's guest is a very accomplished author. He's written a very popular webcomic, yeah, but he's also written comic books. And his stint writing the Adventure Time comic books won him an Eisner and a Harvey Award. His Kickstarter, Choose Your Own Adventure Hamlet book, broke Kickstarter records. And he's refused since then to rest on his laurels. He's currently writing Marvel Comics' hit new book, The Unbeatable Squirrel Girl, and has recently announced a Kickstarter for a new Choose Your Own Adventure book about Romeo and or Juliet. And also recently he notably got stuck in a hole with his dog. Welcome to the show, Ryan North.
Thanks, Ben. All of that was true except for the Kickstarter thing. The Romeo and Juliet book and or Juliet is being published by a natural publisher and not through Kickstarter.
Oh, okay. Do you want me to delete that part?
It's fine.
All right.
We can perpetuate more lies.
Yeah,
sure.
To make people more confused when they want to buy my book.
It's no wonder I couldn't find it on the Kickstarter webpage.
It's not out yet. It's coming in June 2016. Should be in bookstores everywhere.
Fantastic. So, Ryan, for you today, I've assembled two of my very favorite titanium physicists. Arise, Dr. Tia Miceli. Dr. Tia did her PhD at UC Davis, and she's currently a postdoc for New Mexico State University, posted at Fermilab, where she's an expert on neutrino particle physics. And arise, Dr. Ken Clark.
Whoosh.
Dr. Ken did his PhD at Queen's University in Kingston, Ontario, and he's currently assistant professor at the University of Toronto, where he's an expert on neutrino detectors and dark matter. All right, everybody, let's talk about things that stick together.
We're going to talk about fundamental forces, right?
Right, and there's a bunch of them.
There is. There's in fact 4 of them. 4 total. And we already have some of the weird naming that Ben talked about. So if you start from the weakest force, in terms of the kind of strength over distance, that's gravity, right?
Right, gravity is just hot garbage.
Yeah, pretty much nobody cares about it. It holds us onto the Earth, does a bunch of other stuff. Other than that, who cares? Right? Nobody likes that.
Then Ben writes science papers about it.
Yeah, that's fine.
But we're not here to talk about gravity.
Right, gravity's hot garbage, as you said. Okay, so we're working our way upwards in terms of strength. You go up 33 orders of magnitude, you get to the weak force. So it's already really, the naming convention has already put gravity in its place, because it's 33 orders of magnitude weaker than something that we call weak.
Right.
And the weak force really just kind of governs like neutrino interactions and beta decays and stuff like that. It's mostly involved in that sort of thing. But it's fairly...
So this is like room temperature garbage, but not...
Yes, yeah, that's right. We're getting better. And then you go up like, 3 or 4 more orders of magnitude, and you get to the electromagnetic force, which is, the repulsion between like charges and traction of opposite charges and that kind of thing, which, I think probably everybody has a relatively good handle on.
Yeah. Does that include, like, when I put magnets together?
It does. I mean, I don't know if you're going to ask how they work, to do that.
We've all discovered that nobody knows how magnets work. It's
clearly, the internet has outlined that nobody knows how magnets work. Magnets work with the electromagnetic force. That's correct, yeah.
So this is the first of the forces that I can actually observe with my hands and a couple of magnets.
Yeah. So
besides, I guess, gravity I can observe by falling down the stairs.
Yeah, well, that's one way to observe it. I might suggest dropping something, but to each
myself.
their own.
Yeah,
down the stairs.
That's true. Yeah, you did. You really put me in my place there. Yes, good. Okay, so but then if we go to the top force, so like another 2 orders of magnitude stronger than electromagnetic force, that's the strong force. So the most powerful force is the strong force, and this is the one that we're going to talk about. So that's kind of the really brief tour through what we know about fundamental forces.
I'm with you.
There's kind of a mystery here when it comes to classical physics. So you got these protons, right, and electrons. And the reason electrons are stuck to protons is essentially they're in orbit around it because they're pulled together using the electromagnetic force. Opposites attract, one's positive, one's negative, they pull together.
Got it.
The electromagnetic force gets stronger the closer the charges are together, right?
Is that inverse squares?
Yeah, it's inverse square.
Got it, yep.
So in terms of atoms, this kind of makes sense, So if an atom has more electrons orbiting around it, it's kind of puffed out a little bit. It's a bigger thing because all those electrons don't like being that close to each other. So, it puffs out a little bit, right?
Sure. Like magnets.
Yeah, exactly.
Exactly like magnets.
So there's a mystery here, which is protons, right? You got 2 protons in a helium nucleus, or 3 in whatever has 3, what is it, lithium?
I guess lithium comes next.
I guess.
Good job, guys.
You have multiple positive
I'm not
charges.
a chemist.
I know, right? The nucleus of an atom is really tiny.
Yep.
And so somehow, even though the distance between each of these positive charges is infinitesimal, there's a force that can overwhelm that really strong electrostatic repulsion. And so,
that's the strong force.
That's why they call it the strong force, because it needs to be crazy strong.
All right. Well, good podcast. We figured it out.
All right.
Yep, done. Talk to you later.
So the strong force is so strong it can overwhelm all these tiny magnets, if you will, inside the nucleus that want to be further away from each other.
That's actually a good way to think of it, right? You've got these little things that are trying furiously to get away from each other, and the strong force is keeping them in really close proximity.
Sure.
Like glue.
Like glue. But the fact that they're kept together is not even the main aspect of the strong force. It's only a byproduct of what the strong force is actually doing, which is kind of the other really neat part. Because the strong force is really acting on the quarks, which are the makeup of the proton and the neutron.
When you say makeup, you mean intrinsic elements and not surface decoration.
Yes, good correction. The proton and neutron aren't fundamental particles, like, for example, the electron. The proton and the neutron are made up of smaller particles, which we think are fundamental. I'm not willing to go out on a limb and say that they are fundamental, but as of right now, it looks like they're fundamental. And those are called quarks.
When did we discover the idea of quarks?
The late
70s?
60s?
Yeah, 60s, 70s.
Okay, that must have been crazy. Because everyone, I'm sure, at that point pretty much thought that protons and neutrons were pretty fundamental, right? Like, what's smaller than a proton? I don't know.
Yeah, exactly. I mean, people are thinking, okay, we figured out essentially the atom. We've got electrons, we've got protons and neutrons, we're done. Science is over, pack up the bags and go home.
Yeah.
And then, somebody had said, wait a second, how come we can have basically protons changing into neutrons? If those are fundamental, how exactly does that work? And so that led to people thinking, oh, okay, well, turn the lights back on. We have to figure this out. And in doing that, they thought, well, maybe they're made up of smaller particles. And I think the crazy part is, it was proposed in like the mid-'60s and discovered in the late '60s. It wasn't very long between when the theory started and when they actually showed that it existed.
That must have been so satisfying.
I know, because there's lots of things, right? You propose them, and then it's like a lifetime later that they actually get found. But no, this is like 5 years or something.
Because like the Higgs boson took like decades between.
Yeah, that's what I was thinking of. That took forever.
Ken was saying something really fascinating, which is that the strong force, what it primarily does is it sticks the various quarks inside of a proton or a neutron together. And then the reason the protons stick together inside of a nucleus is just because the sticky force, the strong gluon interaction inside the protons, is a little bit leaky. And so if there are two protons next to each other, the strong force interactions inside of one proton might kind of stick to the strong force interactions in another proton and kind of hold them together.
So when you say leaky, is that...
It's a technical term.
Like what you're saying is the strong force exceeds the volume of the thing it's acting upon.
Yeah, that's what he means.
Yeah, the radius of the strong force is larger than it needs to be to just stick the quarks to make a proton or a neutron.
Which is great, because if it didn't, then we'd just have a bunch of protons sticking around without any nucleuses.
Yeah, although I guess we wouldn't be here to be upset about it. So
yeah, I'm not saying I'm upset, I'm just curious.
Maybe we should talk about this in more detail, how we know that there are quarks. Essentially, the short answer is eventually somebody came along with a really strong particle accelerator and detected them. But it's a little bit stranger than that because nobody has ever seen a naked quark. For instance, we detect things. Usually in particle physics, a particle gets created and then we see it. And we're like, all right, that exists, we saw it. With quarks, we've never seen a loose quark outside of its proton-y shell. They don't wander around alone. And part of the reason they don't wander around alone is because the strong force is just so sticky. But we have other means of seeing that definitely quarks are the best explanation, aside from having shot electrons into a nucleus. And it all goes back to kind of the 60s when we were building stronger and stronger particle accelerators. So the deal is, you've heard of E is equal to mc squared. You're familiar with that?
Yeah, it's hot garbage.
Yeah, good hot garbage. It's important in a variety of ways, but one of the really interesting things that comes out of it is particle creation. The idea that you can have essentially no particles. Let's say there's no electrons around. If you shoot two really, really high energy photons together and they smash into each other, the energy density in a little region might be high enough to create an electron and an anti-electron pair.
Do they go their separate ways? They don't annihilate each other?
Yeah, well, they might re-annihilate, and if they do, they'll probably emit the energy into some other form.
Listen, I'm a simple cartoonist, simple country cartoonist, but it sounds like you're saying if you had high enough photons, which are light, that hit each other, you'd get electrons, which when they move can cause electricity.
Yes, that's what I'm saying.
You can generate electricity from light?
Yes.
When I say you, I mean you specifically?
you can create electrons from light, and they're antiparticle.
Have we done this?
Yeah. We do it sometimes, though. I mean, cosmic rays, which are really, really heavy protons and stuff up in space, and they hit our atmosphere, and they hit our atmosphere moving fast enough that it will generate a shower of electrons and anti-electrons.
Really?
Yeah, you generate a shower of particles.
If the energy density in a little region is high enough, you can generate spontaneously a particle and antiparticle pair is an interesting thing. And it underlies a lot of what we're going to be talking about today. So an electron-anti-electron is an interesting thing to start with, for one thing, because it obeys a conservation law. It actually obeys two conservation laws, but one of them is the electric charge, right? So one of the various laws that we know of is that the total electric charge of a system is conserved.
Mm-hmm.
If you rub a balloon on your head and the balloon ends up with a slight positive charge, your head will end up with a slight negative charge.
Sure.
Equal and opposite in quantity.
Right.
How do you know it's not that way and not the other way around?
I don't. But I like to think positive. No, wait. Think negative. Which one did I say ended up on my head?
I don't.
It was negative, I think. We'll fix it in post.
Yeah, that's right. So yeah, moral of the story is you end up, there are these conservation laws that dictate what can be created and why. So when the two photons come in, prior to that, photons don't have an electric charge. If the energy is high enough, if it's going to make electrons, then it has to also make an anti-electron, which has the equal and opposite amount of positive charge.
Right.
So this dictates a lot of fun things, and essentially, early particle physics was a lot of smashing stuff together and seeing what came out.
Hey, we still do that.
I was going to say, that's current particle physics,
What are you
too.
trying to say?
I'm trying to say that it's a wonderful field full of honorable people.
Okay, I like that.
So, one of the goals with particle detectors is to smash things together so hard that you increase the energy density wherever that collision happens.
Wait, I don't think you said that right.
Particle accelerators smash them together.
There we go.
Okay, I'm sorry, everybody.
I'm a simple country cartoonist, but even I can see the distinction between a particle accelerator and a particle detector.
Particle accelerators accelerate particles. They smash together, and the hope is that the energy density where they smash together is so high that it will spontaneously generate other particles.
You said this was fundamental to what we're talking about, so I want to get it solid.
Mm-hmm.
Is this threshold where particles get generated at like a point where if you're just below they don't happen, if you're just above they do, or are we not sure quite what that threshold is?
Yeah, if you're above it, it can happen, and sometimes does.
What? It doesn't happen all the time?
Well, no, right? I mean, that's why they had to smash so many hadrons together before they could see the Higgs boson.
But that's crazy. Why is the universe not deterministic?
Well, it's probabilistic because of quantum mechanics.
Destroying my worldview.
Right? So there's some probability, if the situation is ripe, something will happen.
So you're saying we live in a universe of maybes, where things might happen.
Exactly.
And if we do everything right, we still might not get particles showing up, even though we did everything right.
Yeah.
That's horrible.
Even if you do everything right, you can still fail.
That's horrible.
No, that's fantastic. It allows you to fail and feel good about yourself. You're like, even if I had done everything right, it might still have failed, so it's okay.
Well,
it's not my fault. The universe sucks.
That's right, exactly.
As you go higher and higher in energy at these accelerators, you start to pass by all of these thresholds. So, you can make electrons, then you can make up and anti-up quarks, and you keep on getting to heavier and heavier particles. And soon, the Higgs boson was so heavy, and it was so hard to find, not just because it was produced rarely, but because we had to have such high energy, there was a high probability of producing all of these particles that were below that energy too.
Oh, okay, yeah. So electrons, I guess, are the easy ones, and no one's excited about producing electrons or anti-electrons. But when you're at the levels we're trying to produce Higgs boson, then electrons are just like, whatever, no great stakes.
It's kind of like if there was a random change machine where you put in a bill and then it gave you a random amount of change equal to the amount you put in. So, we were looking for a very special $500 coin. And so we have to put in at least $500 worth of bills, and then most of the time it just gives us pennies.
Yeah,
once in a blue moon, instead of getting a whole bunch of pennies, you'll just get one big coin.
This is crazy. I'm willing to accept it, but I feel like, you guys are all used to this idea. I thought we lived in a world, Newtonian world of cause and effect, and things made sense all the time, and not this random chance that maybe you'll get a particle and maybe not.
They asked God if he played dice, and he said, number one, I have no gender, and number two, yes, definitely all the time. I love playing dice. Do you want to make a bet on something?
You want to bet? So Tia mentioned up quarks, and this reminds me that I think quarks have spins, right? I remember hearing that in my travels.
Quarks have spins.
So quarks do have spins, but up doesn't refer to the direction of spin. It refers to a type of charge.
A strong charge.
Yeah. Hold on. Let me take a step back. Okay.
Did you just take a physical step back?
Literally took a physical step back.
I'm
glad we were all wondering the same thing.
So in the 60s, when they were building these particle accelerators, the higher energy the collisions they can create, the more different types of elementary particles might be generated. So they started seeing a zoo. They classified the subatomic particles in 3 different ways. They called them hadrons, mesons, and leptons.
Okay.
So a hadron is something that's really heavy, like a proton or a neutron. And a lepton is something that's really light, like an electron, or an electron's heavier cousin called a muon. Neutrinos are leptons too. So anything in between was called a meson, which means middle on.
Go on, Professor.
So they started trying to classify the different types of particles that they would generate in these crazy collisions. And what they found was there's a certain breed of particle that didn't quite decay in the normal way. So usually these particles are really unstable, which means that if you can create it, it's fine. It's usually pretty and heavy and weird, but then it pops and turns into other lighter, more common forms of things like electrons.
Right.
So what they saw was things weren't decaying in the way they expected. And when they wanted to start interpreting why these breeds of particles weren't decaying in the way they expected, they had to introduce another type of charge. You know how I said there's like a charge conservation here, where every time you want to make an electron, you always have to make an anti-electron so that the total charge doesn't change?
Yep.
So they were saying, okay, so there's a charge like that. It's not an electric charge, but it's some quantity that our basic elementary subatomic particle has. And anytime the subatomic particle changes into something else, this other type of charge needs to be conserved. So they called that charge strange, because it was strange.
Well, the thing that was strange was the long lifetime those particles
had. They had really long lifetimes because there weren't all that many things it could change into, because it had an attribute, a number, the strangeness quantity to it that limited the number of things it could change into. And so it stuck around for much longer than it should have. And so they're like, whoa, this is strange. Let's call this charge strange. They had to use a different word. They used the word flavor. Electric charge, where there's like some positives and negatives, and the total amount of strangeness in your system of atoms that are decaying or creating has to be constant.
Okay.
So the moral of the story is this introduced this idea that there was some attribute of these particles that wasn't in the more common electron, proton, neutron particles.
Right, because those don't have flavors that we know about.
Yeah, well, they all have some kind of common flavor to them, so you're like, all right.
Right.
They didn't have the strangeness.
So they're all, if you will, vanilla particles.
Right.
Very well done.
So you essentially see a lot of different particles, and so they started classifying them in terms of how much electric charge they have and how much mass they had, and what they saw was kind of a pattern that looks kind of like the periodic table of the elements. And so one of the things the periodic table of the elements tells you is that there's kind of an underlying structure that are common to all these chemically different elements. You can say, well, the difference between a hydrogen and a helium is that helium has one more electron, one more proton, right? Its mass is twice as big. And you can start talking about the different atoms in the periodic table in terms of being composed of protons and electrons. And that kind of explains the different general properties, why it's laid out in that way. So they were doing this with subatomic particles, and you end up with a similar pattern that kind of indicates that there's some underlying structure, that the mesons and the hadrons are all composed of smaller little bits of Lego, that these mesons aren't fundamental particles the way an electron is.
Is there a periodic table of subatomic particles?
Yes.
It's called like the eightfold way, right?
Yeah, we still use it. Oh, no. So the eightfold way was just if you permute the charges up, down, and strange. So you can have up, 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 down, 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 up, down. You know, and you write...
Up, strange.
Yeah, and you write down all of those. You can organize them into this sort of triangle. And then that's for the baryons. And that was the chart that was sort of like the periodic table.
And do all those exist? Like if I want up, down, strange?
So actually, one of the ways that we knew this was definitely true was from mapping out all of the permutations they predicted that they should see a strange, which was the omega minus. And
omega minus.
Yeah.
That's the best name for anything ever.
So when we actually found that, it was pretty controversial before, like eightfold way, substructure, what are you talking about? But then, okay, you predicted this particle. I believe you now.
Yeah. And I made a prediction that came true, so we believe that this theory isn't hot garbage.
Yeah, right. Not like gravity.
Not like gravity or relativity.
Yeah, right. So the moral of the story is that the study of the zoo of elementary particles told us two things. One of them is it looked like you could explain all of the different types of subatomic particles you would generate in these colliders. You could explain them in terms of an underlying structure, some combination of different little Lego pieces, where one Lego piece is called up, one of them was called down, one of them was called strange. And it was like, okay, so it looks like the different permutations and combinations of these little bits give you all of the different subatomic particles we're detecting. And that was interesting. And so what you could do is you associate the up quark, the down quark, and the strange quark all have very specific charges and spins, right?
Yeah, up, charm, and top have plus 2/3 electrical charge, and the other guys down, strange, and bottom have minus 1/3 electrical charge, and they'll all spin half.
Right. So a proton is, what is it, 2 ups and a down?
Up, down, yeah.
Up.
Because then when you add up all those, it's 2/3 plus 2/3 minus 1/3, total charge 1. And a neutron is 1 up, 2 down. So it's plus 2/3 minus 1/3 minus 1/3 equals 0. And it also explained all of the different charges of mesons, which might have different electric charges, because one meson might be 2 ups together, another meson might be an up and a down, right?
Sure, yeah.
Okay, so mesons, let's clarify a little bit. They're made up of a quark and an anti-quark pair. So it's actually a bonding between the quark and the anti-quark.
Quark and anti-quarks don't mutually annihilate?
So that's another interesting question. Not all the time. And
some of the time?
Well, for a really long time, that was one of the defining mysteries in particle physics was, okay, so I have this particle called a pion, a 0 pi, and it's made up of an up quark and an anti-up quark. And so why doesn't it annihilate itself? And it will annihilate itself after some time, but that's due to like quantum fluctuations after a long time.
Right.
But it's mostly stable. The answer is the same reason why electrons don't just fall into the nucleus. That you have some internal interactions going on between these two quarks.
So they're metaphorically in orbit around each other, but not colliding.
Yeah.
Right, but pions do decay into 2 photons, don't they?
Yeah.
I mean, they do eventually annihilate. But what T is saying, I guess, that there's a reason why it doesn't happen immediately.
Yeah. Why they're allowed to be formed.
Why we allow these things to exist at all.
So, moral of the story is, there are different quarks. So far, we've got 3 different quarks, and they're antiquarks, right? And all of the particles that we are familiar with, like protons and neutrons, but also all these weird particles that were generated in the early 60s particle accelerators, can be explained in terms of some combination of the quarks, up, down, and strange.
Yep.
So, 2 things to go on from there. Eventually, they built a particle accelerator, I think in the 70s. It was accelerating electrons, but they were going fast enough that they could penetrate the inside of a proton or a neutron. And so inside, what they saw was that there was clusters of electric charge, 1/3 and 2/3, just like we'd expect in this quark model. So we've experimentally detected evidence that the inside of a proton does have 3 little bits of charge. The inside of a neutron does have 3 little bits of charge.
So we're feeling pretty good.
So we're feeling pretty good about this quark model. Then the story is, this strange thing, how come we don't see strange subatomic particles in regular life? Like, how come there aren't any strange atoms chemically? And part of the reason for that is that we talked about how there's kind of an energy threshold beyond which a certain type of particle and antiparticle would start randomly getting generated. So the deal is that the strange quark is heavier than the up and down quark. And so you couldn't start seeing it until your accelerators got energetic enough to exceed that energy threshold and would start randomly generating them.
Sure.
So since then, as the accelerators got more and more powerful, they could exceed these higher and higher energy limits, and they started seeing other types of quarks. So there's up-down, they're a pair, right? One of them has plus 2/3 charge, the other has minus 1/3 charge,
yep.
right? So the strange has plus 2/3. It has a companion that has minus 1/3. There's a charm flavor to go along with the strange flavor. So then the last two are even more energetic and required even more energetic particle accelerators to generate. Their labels are T and B. And it's funny because it depends on whether I've heard as to what those initials mean. They're called top and bottom. So top is the plus 2/3 charge, electric
bottom
charge,
is negative
minus third, right? We discovered the bottom one, and then the top one finally got discovered in the 90s. But in Europe, they're called truth and beauty.
Oh, it's so good.
I know, right?
Way better. So is this a ceiling? Can we expect to find more pairs of properties? Or do we have a reason to think that this is it?
No, we have no reason to think this is it. I mean...
Wait. Okay, hold on. I was trying to think of this before. Isn't there something about electroweak unification that requires the same number of quark families as lepton families? I'm pretty sure there's something that at least suggests we have to have the same number of families in both.
If you're referring to a theory, I don't trust it. I only trust experiments. So the reason why there could be something that we haven't seen yet is just that we're limited by what our particle accelerators can do. If we can have another couple $1 billion, we can build a more energetic particle accelerator, and maybe we'll find some more families. Actually, at the LHC, they do searches for more heavy quarks called T prime or B prime. They haven't found anything.
They could maybe show up, because there's always a chance, right?
Yeah.
If these were discovered, we wouldn't still call them T prime and B prime. We'd call them new names, right?
Yeah, what should we name them?
Can we name them now, and then when they're discovered, we'd be called dog and cat?
No, the D initial is already taken, right? Because you need two letters.
Yeah.
Okay, hot or not, H and N. That'll be my contribution to particle physics.
I think that's keeping with the charm and strange pair, yeah.
We got strange and charm, truth and beauty, and hot or not.
Yeah. But Ken was saying that we're pretty sure that there's only 3 families of leptons. So electron, muon, and tau particles. And they're all fundamental particles in the theory. So there's 3 of them. And then they have those similarly flavored neutrinos. So there are electron neutrinos and muon neutrinos and tau neutrinos. And so Ken's argument is essentially somebody argued that because at really, really, really high energies, the strong force and the electroweak force are all supposed to be 2 aspects of the same force. There needs to be the same number of types of families of flavors of quarks as there are electrons.
Sure. And that's sort of a let's hope the universe makes a sense to us sort of argument.
Yeah, that's right. And it might. When people make these guesses, sometimes they're super right, and then when they win Nobel Prizes. So essentially, we got this nice theoretically proposed and then experimentally verified substructure defining all these different types of subatomic particles in terms of these quarks that are sticking together. But how and why they stick together is totally bananas. Let's start talking about that.
They stick together by something called gluons.
Gluons.
So these are the mediators for the strong force. So you were saying you can smash 2 photons together and produce electron and positron. So it's the same thing with the gluons. You can smash 2 of them together and produce, for example, an up quark and an anti-up quark. So they help facilitate quarks interacting with each other. Another cool thing about them is that they don't care anything at all about leptons. They only interact with quarks. So we have 6 quarks, and we have our gluons.
All right, let me try backing this up. So in theoretical quantum field theory, when 2 objects interact, they interact by essentially playing catch with an invisible particle. Okay? So when two electrically charged particles, a proton and an electron, interact with each other, they do so by throwing a photon back and forth. And that quantizes the interaction.
Wait, this is literal? This is literally what happens? This is not a metaphor?
Well, it's kind of a metaphor. It comes from a numerical approximation to the actual theory, which is quite complicated. This is like Richard Feynman. So Richard Feynman's like, hey, instead of trying to solve these crazy equations, let's just talk about it in terms of approximations of more and more complicated interactions where the interactions are all mediated. And so this is what a Feynman diagram draws. It essentially says, all right, you got this electron, it's over here, it tugs on the proton over here. How does it tug? It shoots a little photon between them. And so you draw a little line and you say, that's the photon, and they do their thing.
Okay, that's cool.
So in this case, we have these two quarks, and they stick together by throwing back and forth. They're exchanging one of these gluon particles. The crazy bit here is that in electromagnetism, there's two different types of charge, right?
I'm with you.
In these strong force interactions, there's three different types of charge. This is the reason you have three different quarks inside of a proton or inside of a neutron, because those three, one has each type of charge and they're sticking together to become an overall charge neutral object. So they were like, okay, so what are we going to name all these charges? And somebody 1970s, right? Somebody was like, all right, man, color theory. This is the best thing. We're going to name one of them each of the different colors that all add up to white. So one of the charges is called red, the other a blue charge, the other a green charge. And they stick together to make an object that has an overall white charge. The desire here is, if you have a group of objects where the total amount of charge adds together to make white, then that won't really exert too much strong force on any other thing. So if you have one atom of hydrogen and another atom of hydrogen, their protons won't pull each other together because each of those protons is white. In terms of this charge. So it's absolutely bananas. You get all sorts of really crazy things. Like we were talking earlier about mesons where there are two quarks. So one of them is red, say. So for the particle to be white, the other one has to be anti-red.
What is anti-red?
Yeah, what is it? It's cyan, right? So it's a color opposite red on the color wheel. And so red plus cyan is equal to white, no color.
This is garbage, because colors don't work that way. This is a stupid metaphor. I may be a simple country cartoonist, but this is a bad metaphor, because it gains you nothing and only makes things more confusing, because red and cyan do not give you white in any color system, except for this particle physics color system.
No, that's not true. In light, if you were a stagehand and you controlled the lighting system, and you only had a red light and a cyan light, you can make a white spotlight by mixing them. So that's legitimate.
Am I wrong? Is this what it feels like to be wrong?
Yeah, so it's the difference between like additive color theory and subtractive color theory. I forgot which one is which one, but one is for lights and one is for like painting and coloring.
Yeah, painting is all the colors give you black.
Yeah.
And light, all the colors give you white.
Even though it's an analogy, it's kind of cool only because it makes the math a lot simpler.
I didn't mean to interrupt. I just looked it up, and I see what they're saying. They're saying that cyan is the combination of blue and green. So when you have red and cyan, you're essentially having red plus blue plus green, so it does equal white.
Oh, okay. I guess I should take back some of what I said about particle physics being stupid.
Well, at least for this reason. I mean, you don't have to take it back entirely. Just the justification's going to have to be different.
Yeah. Well, if the metaphor holds, then that is at least not a actively fighting against you metaphor.
So yes, yeah, Tia, you are correct.
Yeah, I know I'm right.
So the strong force is really crazy because most forces get weaker the farther away you get, right?
Yep.
The strong force gets stronger the farther two things are apart.
What, indefinitely?
Well, here's the thing. We've never seen a naked quark, and the reason is because of the strong force. So, thought experiment. Let's imagine it in terms of a spring, right? So a spring, the more you stretch it, the more it pulls together, right? So you imagine these two particles, one of them is anti-red, cyan, and the other's red, and they've got a gluon sticking them together. And then take out your tweezers and you're like, hey, let's see what this thing is made of. And you pull them apart and you start stretching them apart. The more you stretch it, the more energy the spring has, the more potential energy we need to put into the system.
Yep.
And the deal is the strong force is really strong, so the farther we pull them apart, the more energy it has until the energy threshold for creating a pair of quarks is exceeded. And then once that happens, spontaneously you get a quark-antiquark pair popping into it. And essentially, you'll end up with two systems of two particles instead of one system of two particles. So anytime you try to see a naked quark, anytime you would try to drag one away, it requires so much energy that it will spontaneously generate a new pair of quarks to fill in the gap. And you'll end up with two sets of white charged objects.
So it sounds like it's impossible to see a naked quark, given our current understanding.
Yeah, no, I don't think we'll see them ever. I mean, oh no, this podcast is going to go into the archives, and, you know, some physicists like 1,000 years in the future will be like, ha ha ha, she didn't know, but we made this amazing detector that can see naked quarks.
Well, that's why I said, given our current understanding.
Yeah.
Cover ourselves for those 1,000-year in the future physicists who just want to, like, prove that podcast wrong.
Yeah. There might be one of those out there, but I wouldn't bet money on it anytime soon.
Okay.
You'd be better off playing the lottery.
Well, that was great. Thank you, Tia. Thank you, Ken. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here is some fruit. Tia, you get apple slices from my school's cafeteria.
Yum.
They're red. That's right. And Ken, we had these ones left over. These are apple slices from my school's cafeteria that are anti-red.
Does that mean they're anti-yum?
Yeah. Right. Okay, I'd like to thank my guest, Ryan North. Thank you, Ryan.
Thank you for having me. This is great.
Listeners, you guys can find his webcomic at quants.com, and you can buy Squirrel Girl comics from your local comic book store, or that new Romeo and or Juliet coming out next year. Fantastic. Hi, everyone. This episode was pretty fun, huh? Okay, time for the announcement. Lots of good news. Now, first, I was thinking around this time of year, people go around poking for new podcasts to listen to while they sit in the airport or on the bus or on their long car trips to visit their great aunts, and it's time to remind the world that we exist. So I've got a plan. The paper that Dave and I wrote about how to make a TARDIS, it's been published in a book called More Doctor Who and Philosophy. It's a sequel to a book called Doctor Who and Philosophy. It's not More Doctor Who and More Philosophy. Anyway, moral of the story is the publisher sent me a couple free copies. From December 1st to December 15th, there are 2 ways to win a book. Now, if you find us on Facebook and interact with our Facebook page in any way, your name will be entered in a draw for the book. Reblog our stuff, tell your uncle about us, like our episodes, whatever. I'll pick one of you at random and send you a signed copy of the book. Now, the second way is give us an iTunes review, then send me an email at tiefighter@titaniumphysics.com to notify me when you've written a review, and I'll enter your name in a draw, and the winner gets a signed copy of the book. Now, even if you wrote your review 2 years ago and you can't update your review, I mean, you can, but it doesn't count as a new review. Who knows how iTunes works? Just drop me a note, and I'll enter you in the draw. But, you know, anyway, moral of the story is lots of you haven't written iTunes reviews, and that's fine, but if you do, we shoot up the charts and more people discover us just in time for that long car trip to their great aunts. Now, in other news, transcriptions are firing on all cylinders. We've got about a dozen done, and many more out there being written as we speak. Email me if you're interested in trying your hand at transcribing an episode, and we'll talk about the details. On that note, we're still humbly soliciting your donations. Your donations go to paying for server fees and our ambitious projects to get all the episodes transcribed. This particular episode of The Titanium Physicist has been sponsored by a collection of generous people. I'd like to thank the generosity of Melissa Burke, Yassine Ouarzazi, Spider Rogue, Insanity Orbits, Robin Johnson, Madame Sandra Johnson, Mr. Jacob Wick, Mr. John Keys, Mr. Victor C., Ryan Close, Peter Clipsham, Mr. Robert Halpin, Elizabetha Teresa, and Paul Carr, Mr. Ryan Newell, Mr. Adam K., Thomas Charrier, and Mr. Jacobs S., and a gentleman named Brett Evans, a lady named Jill. Thanks Steve, Mr. James Clausen, Mr. Devin North, a gentleman named Scott, Ed Lowlington, Kelly Wienersmith, Jocelyn Reed, Mr. S. Hatcher, Mr. Rob Abrazado, and Mr. Robert Stietka. So if you want to donate, you can donate one-time donations on our website or through Patreon. So that's it for Ti-Fi this time. Remember that if you like to listen to scientists talk about science in their own words, there are lots of other lovely shows on the Bracula Media Network. The intro song to our show is by Ted Leo and the Pharmacists, and the end song is by John Vanderslice. Good day, my friends, and until next time, remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hop down Magnolia Boulevard. No way he'll survive.
Do we know what gravity is besides a force?
In terms of, like, do we know what...
It's the curvature of space-time.
But, like, gravitons don't exist.
Gravitons are a linear approximation for the force of gravity. And so they exist when people try to quantize gravity, but nobody knows how to quantize gravity. So...
Yeah, this is really Ben's area.
So we think that somebody eventually has to figure out how to quantize gravity, but nobody knows how to apply quantum mechanics to gravity because the theory of general relativity, the theory of curved space-time, is like it doesn't work. It's like when you plug.
It's like
when you plug.
There's the pull quote. Theory of general relativity. It doesn't work.
I like that.
It's like when you plug a 1998 webcam into your computer. It's just like does not understand what I'm talking to, and you're like, oh, I shouldn't have saved $15 like that. Yeah, it doesn't work at all. They're too, the theories are too different, and you get weird infinities popping up everywhere.
Okay, so gravity. Sorry.
If you did manage to quantize gravity, you would describe the interaction in terms of gravitons. So they show up, people talk about them as if they're going to show up on store shelves next year, but who knows?
You never know.
So when Star Trek talks about graviton emitters, that's actually really good science fiction because it's predicting something that we're expecting to invent.
Yeah, it's
not discover, invent.
Yeah, it's a word from science. And they added a fictional element to it.
So it's science fiction. I like it.
That's
right. Perfect. Star Trek is right, and Einstein's relativity doesn't work.
That's right.
All right.
That's what they're saying.
This makes me feel good about my life choices. So I know way more about Star Trek than I do general relativity.
Oh, a graviton emitter. So that would be like anything that gives off gravity waves. So like a binary system?
No, but I think they mean anything that produces gravity because...
Well, they use it as a tractor beam.
Yeah.
And they put it in reverse. They have reverse gravity to push things away.
Oh, that's pretty clever.
It's just anti-gravitron. Graviton. Gravitron is a thing you ride at the fair.
It's a pretty fun thing, yeah.
I just had this debate with my class of second years, and none of them knew what it was. I was really upset. Yeah, I actually had to put up a picture on the screen in class and say, this is what it is. Nobody got it.
Wow. If I was in your class, I would have been a star student.
Yes. Yes, you would. No doubt about that.
So I want to ask the three of you, do you think the fact that the research into quarks and the discovery of quarks and their naming and stuff happened in the late 60s and 70s is partially responsible for them having such ridiculous names?
I would say 100%.
No, I think the fact that it's physicists trying to name things gave them ridiculous names.
But I mean, physicists named other particles, like electron was probably named by a physicist, and that sounds pretty normal. It's an on that is electro.
Yeah.
As soon as I hear, like, Charm and Strange, I think, like, a bunch of dudes with big mustaches and paisley shirts sitting around. Oh, yeah, man.
All this Charm and Strange.
Yeah.
It's probably the most dated physics term I've ever heard.
Well, quark in itself is already kind of a strange one too, right? But
yeah, that sets the tone for what follows after that. And if they called it a boring particle, just call it the boring particle. Then there wouldn't have been all these other cool names attached to it. You'd have like gray and off gray,
and taupe and beige.
Yeah, beige and anti-beige.
I'm glad you guys weren't the particle physicists back then.
I think Tia's right. It's probably that we're just horrible nerds. I guess if you had one in a universe where there was only a single quark, then it would have nothing to pull on, and you wouldn't have. It could be naked alone. But as soon as
that's not your universe.
How do you create a universe
general relativity? You start speculating. No, you're right.
That's what Ben does all day: is create universes.
That's right.
Universes of the imagination.
I should start wearing a turtleneck.
We're not so different, you and I.